Here in this video, we're going to look at three more examples of integrals involving our inverse trig functions. And the first one is we want to find the integral of 3 over 2 times the square root of x multiplied by the quantity 1 plus x dx. And probably looking at the three examples formulas above here, we notice we have the square root in the denominator for 1 and 3, and number 2, we simply have a squared plus u squared. So it looks like we would probably fit this to the arc tangent. So if we're trying that, it looks like if we focus on this 1 plus x, if we think of the 1 plus x to be our a squared plus u squared, then it looks like we're going to let a equal 1. And then it looks like we would let u equal, now be careful, if this is a squared, so the square root of 1 is 1, and then we have x. So if this is u squared, then that means u must be the square root of x. So u is equal to the square root of x. And then if we take the derivative of u, we would have 1/2 x to the negative 1/2 dx. And it may be helpful here to rewrite this as 1 over 2 x to the positive 1/2, or we could think of this as 2 times the square root of x. Now, if we do that, do we have our du? Well, 2 square root of x dx. Well, here we have 2 square root of x dx. So all of that is our du. And it doesn't look like we need the 3, so we could certainly move the 3 out front. So we'd have 3 times the integral of dx over 2 square root of x. Now I'm going to actually group this together over here. So we have our dx over 2 square root of x, okay, because that's going to all be our du. And then we have 1 plus x. So we could think of this as 1 squared plus the square root of x squared. So 1 squared plus the square root of x squared. And now do we have our formula? Well, we could think of this here. We have our du, dx, 2 square root of dx, that's our du. So all of this is our du over a squared plus u squared. Well, we have a squared plus u squared. So it looks like we have our formula, so then we can plug in. Don't forget to bring down the 3. So if we bring down our 3, and then we have 1 over a. Well, 1 over a is 1 over 1, so that's just 3 arctangent of u over a, and our u is the square root of x over 1, so that's just simply the square root of x plus c. So at first that looked a little more complicated, but once we identified a and u, the du kind of fell right into place. Now I do want to look at this problem in another way. I want to look at this one, if we weren't able to see it that way, what if we were to simply use complete u substitution here? So in other words, if I was to let u equal the square root of x, then du would have certainly been 1/2 x to the negative 1/2 dx. Or we could think of that as 1 over 2 square root of x. Now if we try to use complete substitution here, then that means we want to solve this for dx. So if we were to take our du here, we solve this for dx. If I solve this for dx, then I'm going to move everything else to the other side. So if I'm going to get rid of 2 square root of x, I've got to multiply that over here. So that means we would have 2 square root of x multiplied by du. And then if we look carefully, what is the square root of x? Now we're trying to get everything in terms of simply u and du. And here we have the square root of x. Well, up here we know the square root of x is equal to u. So we could write this as dx equals, instead of 2 square root of x, we could simply say 2u du. So now if we plug this into our formula over here, we have the integral. Still the 3, we can simply pull the 3 out front. And even the 2, we can simply pull that out front, so we have 3 halves. And then we have dx. Well, what is dx? Well, dx is equal to 2u du. So we're going to substitute that in, so we would have 2u du over, now the 3 halves we've pulled out front, so we have the square root of x. Well, what is the square root of x? Well, the square root of x is equal to u. Okay, so right here, square root of x is equal to u. So that becomes u. And then we have 1 plus x. So that would simply be 1 plus x. Well, what is x? Well, if the square root of x is equal to u, then if we square both sides, that means u squared is equal to x. So we would get 1 plus u squared. Now, if you notice here, if we simplify this, our u's are going to cancel out. So we would certainly just have 3 halves times the integral of du divided by 1 plus u squared. And here we can see this definitely fits the arc tangent. Du over 1 plus u squared, du over 1 plus u squared. So we're going to let a equal 1. And then here you have our u squared. Okay, so if we plug this into the formula, we have a plus our u squared and our u and our du. So if we look up here, we have 3 arctangent square root of x Oh, one other thing here. We have forgot to cancel this out. We have our 2 here. This 2 and this 2 would cancel. So all we're left with out front is the 3. So we can bring down the 3. We would have our 3. And then our formula says 1 over a arctangent u over a. So in this case, we would just have a as 1. So 3 arctangent. Okay. Arctangent of u. Well, u is equal to what? We said u is equal to the square root of x. So then we would simply have the square root of x over 1, or simply the square root of x plus c. And that's the exact same answer we came up with before, 3 arctangent square root of x plus c. And we've only done a few examples like this here where we did the complete substitution for all of the variables. Most of the time we can identify, like the first way we work the problem, we can kind of fit the pattern here without doing the complete substitution. But I just want to remind you here, we can go through the complete substitution to set up this problem. All right, here we have another example. The integral of 4x plus 3 over the square root of 1 minus x squared. And you'll probably look at this and say, well, we could certainly just let u equal x and a equal 1. But if we let u equal x, because remember this is a squared minus u squared, but if we let u equal x, the derivative of u would be 1x, and we have all this extra variable 4x plus 3 on top. So that's not really going to work. So here we're going to have to use one of our techniques we've learned in the past, and that is to split this into two integrals. So if I split this to 4x over the common denominator, 1 minus x squared, and then I can take and add that to the second integral, take the 3 over the common denominator, square root of 1 minus x squared, and we can look at these two separately. So let's start with the first integral. We have 4x over the square root of 1 minus x squared. So it looks like we could let u equal x and a equal 1, but again, if we let u equal x, we still have this 4x on top, because if we let u equal x, then du is 1, but we can get rid of the 4, but we can't get rid of the x here. Now, the first integral, I'll give you a hint. We're not going to use our inverse trig functions. We're going to use this as just a basic u substitution. So here, we're going to simply let u equal 1 minus x squared, and then du is going to be a negative 2x dx. So if we look over here, we have a 4x dx. Well, we need a negative 2x dx. Well, we can certainly take care of that. We can take and multiply by a negative. Now, because we don't need the 4, we just need a 2. I'm going to take 2 times 2 is 4, so I'm going to factor out one of the 2's and move that 2 out here, and that leaves me with 2x dx. Now, do you see what I did here? I'm not dividing by the 2. All I did was split the 4 up into 2 times 2, and I pulled out one of the 2's. And then we need a negative, so I'm going to multiply by a negative on the inside and then a negative on the outside. And then on the bottom, we're still left with the square root of 1 minus x squared. And what do we have at this point? Well, negative 2x dx, that is all our du. Negative 2x dx is du over the square root of 1 minus x squared, so that's over the square root of u. So really what we have here is negative 2 the integral of du over the square root of u. And if we rewrite this, we'd have negative 2 the integral of u to the negative 1/2 du. So now we can simply integrate this, bring down our negative 2, and if we integrate, this would be u to the positive 1/2, because we're going to increase the exponent by 1. And then we divide by a half, but if we divide by 1/2, we're going to multiply by the reciprocal, which would be 2. So then we're left with a negative 2 times 2, which is 4, u to the 1/2, and remember u is 1 minus x squared, so that would be 1 minus x squared raised to the 1/2 power. So now there's our first integral. So let's go back and look at the second. We have 3 over the square root of 1 minus x squared, and this one looks like it's going to fit one of our inverse trig functions, and I'm going to look at the formula of du over the square root a squared minus u squared. And this is going to be equal to the arc sine of u over a plus c. All right, so now we need to identify what is a, what is u. Well, it looks like obvious enough, hopefully, you can tell that a is going to be 1 and u is going to be x. And if we take the derivative of u, we're going to simply have 1 dx. So here, we don't need the 3, so we can pull the 3 out front. So we have our 1 dx over the square root of 1 squared minus x squared. And again, this is 1 squared, so our a is 1, so a squared minus u squared. So at this point, if we do the actual substitution here, then we'll see that we have our 1 dx is simply our du over the square root of a minus u squared. So we certainly match up exactly with our formula over here. So then we simply bring down the 3, and then we would have arcsine of u over a, so that's x over 1, so that's the arcsine of x, plus c. So I would bring this down here, and with our first integral, we'll just simply add 3 arcsine of x plus c. And you notice I didn't put a plus c with this first one because that would give us a constant, and then I'd have a constant with the second one. So I could certainly add those two constants and just have one constant for both of these terms. So there's your integral. And the reason I wanted to look at this one is to remind you to look at other techniques. Don't forget all the techniques we've learned in the past. Here we couldn't just use basic u. We had to separate this into two separate integrals with our common denominator. And then the first integral was a basic u substitution, whereas the second integral was using your u substitution to fit one of your inverse trig functions. And in this case, it was the arcsine. All right, one more example here. It says use the differential equation and the specified initial condition to find y. So basically, we have our differential equation dy dx is equal to 1 over 4 plus x squared. And they give us that y of 2 is equal to pi. So now y of 2 equals pi, what that really means is when x is equal to 2, our y value is pi. So we want to use this given point to help us solve this differential equation. So if we know that we're going to solve this, then dy dx we're going to integrate, and the integral here of dy would simply be y. So that means we need to then integrate 1 over 4 plus x squared. Now hopefully this looks a little familiar to you. It looks like we have 1 over 4 plus x squared, so it looks like one of our inverse trig functions. And if you go back and look, I think because there's no square root here, this is going to be the tangent, where we have du over a squared plus u squared is equal to 1 over a arctangent of u over a plus c. So do we have all the pieces that we need? Well, we could let a equal 2. U is going to be equal to x, and then of course the derivative would simply be 1 dx. So it certainly looks like we have everything that we need. We have our dx, our a squared plus our u squared. So we simply plug into the formula 1 over a, so that's 1/2 the arctangent of u over a, so that's x over 2, plus c. Now, normally this is where we would stop, but they tell us that up here, when x is 2, y is equal to pi. So that's where we're going to use our point now so that we can solve for c. So when y is pi, we get pi equals 1/2 the arctangent of x over 2. So that means we would have 2 over 2, or simply 1. And now we can solve. So we would have pi equals 1/2 times, well, the arctangent of 2 over 2. Well, the arctangent, that's going to be either 45 degrees or simply pi over 4. So then we would have pi equals pi over 8. And then if we solve for c, we're going to subtract pi over 8. So 1 pi minus pi over 8 would be equal to 7 pi over 8. So then we can plug this is our c value, we can plug this back into our equation up here. So we would end up with y equals 1/2 the arctangent of x over 2 plus, instead of c, we're going to plug in the 7 pi over 8. So that's how we can solve for a specific solution here for the differential equation given that y of 2 equals pi. Now, if they didn't tell us that when x equals 2, y is pi, then we would simply leave this as plus c.